So for this hands-on session, I thought about two different notebooks. One will show you what is possible to do now on ClimaOcean, so all the possible interaction between different components. And in the second notebook, I thought we could actually build a new component from scratch and couple it to an atmosphere. So the idea is to actually have to construct a slab ocean that just evolves temperature in one layer and couple it to a sea ice model and then a speedy weather atmosphere. I don't know if we'll get there, but I guess the first notebook will be a little bit more faster. I'm gonna go through and demonstrate a little bit how ClimaOcean works, also because as you'll see, ClimaOcean takes a while to precompile, and there's also data that is required to run these simulations in the first notebook that will be automatically downloaded on your laptop, but it will require some time. It will depend on the internet. So I'll go ahead quickly, and if you want, you can follow in your time, and then I'll move on to the second notebook, and we'll look at how to build a new ocean component. Yeah.
If you want to follow this, do we need a GPU?
No, this is fully CPU. This runs on a laptop and it's pretty fast. The only problem is pre-compilation or time to first time step, let's say. So the notebooks can be found in the JuliaEO GitHub page under Notebooks Day 4 ClimaOcean. Please instantiate the project.toml that is in that folder, because it has, I'm using a branch of ClimaOcean for this notebook that some features are not yet merged in main, so use that branch. Okay, so in this notebook, I'll show you how to use ClimaOcean, how to add an ocean, a sea ice, an atmosphere, and run a coupled simulation. This is a little bit of generated text from AI. So you should be able to once you have the notebook, to activate the directory that you have, activate the directory where you have downloaded the notebooks with the project.toml and the manifest.toml. You'll probably need to instantiate. Yeah. Can you change that?
Change the font size. Maybe just change the light. Can you switch the
We'll make it to white.
Yeah, switch the light. Light versus yeah, lighter.
Better? Okay. So when you instantiate, make sure that ClimaOcean is on this branch, which should be already encoded in the project.toml, but just make sure that this is the case. And we start with building an ocean model. Maybe I'll wait for a second for everybody to download.
Sorry.
To download.
The problem is with the recording, but
Yeah.
Başka bölümde mesela bu sokaklarda bizim.
okay. No, mas
Okay, so we start with an OMIP simulation. So ocean, sea ice on the same grid, tripolar grid, and atmosphere that forces on top. So this example is meant to run on a CPU. So we specify the CPU architecture in Oceananigans. If you have a GPU on your laptop, you can do using CUDA and arc equal to GPU, and this example will run on GPU. I don't have a GPU available here, so I'm just going to go on the CPU. Now, for the grid dimension, we're using a pretty coarse ocean to make it run on the CPU. So this is 120 points in the meridional direction, 60 points so 120 in the zonal direction, 60 in the meridional, and only 50 in vertical levels. You see here that the vertical levels are pretty stretched, so we're looking at 600 meter resolution, which is very, very coarse. So I wouldn't advise to run a production ocean model with this resolution, but for a demonstration, this is enough. And we create the tripolar grid, which is that kind of weird grid that has the North Pole stretched in Canada and in Russia, so that we avoid the problems with singularities. And here we go. Oh, what? First problems. Speedy weather.
Oh.
I think I loaded it. Yeah. Yeah, it would be a good idea. Now we created the tripolar grid with 160 by 60 by 15 points. Actually, let me show you the actual tripolar grid type. There's the tripolar grid, and it's an orthogonal spherical shell grid. We're running with float 64. We can also go on float 32. It's centered at this location, and it has a periodic longitude and a connected latitude, because the latitude kind of folds on top of itself, and a bounded vertical direction with variably spaced spacings. Now we need to add a bathymetry. So ClimaOcean provides this grid bathymetry method that will automatically download eTopo 22 data. That is a bathymetry at 1/60th of a degree resolution, and we'll regrade it on the grid of choice, which in this case is the underlying grid. We specify here a certain minimum depth of 100 meters. That really doesn't matter because our first cell is at 690 meters. So probably I could have avoided this keyword argument. Measure basins equal 1 means that we're gonna fill in all the lakes and all the closed basins except for the biggest one, which is the ocean. And we use some interpolation passes because we want the bathymetry to be a little bit smoother. The more passes you use, the more you smooth out the bathymetry. Probably not the best way to smooth the bathymetry, but it's definitely the simplest. And we take the bottom height that comes out from this grid bathymetry, and we insert it in our tripolar grid, building an immersed boundary grid. So immersed boundary grid is a grid where certain cells are going to be inland and other cells are going to be active cells, where you compute the actual equations of motion. Almost done. Okay, here we go. So this is our immersed boundary grid. We can visualize our bathymetry. That looks something like this. So a little bit coarse-ish, but this is the resolution that can run on the CPU. Okay, so now we have the grid and the bathymetry. We can start configuring the ocean simulation. Oceananigans gives you a lot of choices in terms of parameterizations and numerical schemes that you can use. By default, we're using a RK3 time stepper and some quite advanced numerical scheme for advection that are very heavy. So in this case, since our simulation is very coarse and we don't really care about the fidelity right now, we're going to use very simple centered schemes for advection momentum tracer. And an important thing when you're configuring ocean simulation is to give the correct parameterizations. So in this case, we're using CATKey, that is parameterization that we calibrated based on LES simulations that accounts for vertical mixing in the ocean. So when you have convection or winds that blow on the surface, you have deepening of the boundary layer and turbulence that will mix the waters. So you need some way to represent it. And this is what this default ocean closure does. Now, since we're using pretty crappy advection schemes, we need to provide some diffusion to the model, because otherwise, if left unchecked, the errors in the numerics will propagate and eventually crash the solution. So we're adding a scalar-aware biharmonic diffusivity. So basically, an operator that is lambda squared. That is depending on the cell area squared, divided by a certain time scale. Okay. With all these parameters, we can start building the simulation on the ocean grid with a certain closure, trace advection, moment advection, and well, this is just a flag for performance optimization that pre-computes the buoyancy gradients. This will probably take a while on your laptop because pre-compilation is not that great. Here in this step, we're allocating all the prognostic and diagnostic variables, all the memory, and setting up all the simulation. Which is taking a little bit. I thought I pre-run it. Maybe I changed something. Okay, so we created an ocean simulation. Actually, I can show you how it looks like, because we also try to have, how do I create a row below this? So, oh. This is a simulation that will have a model attached to it. And this is a hydrostatic free surface model. And here you see all the details of the model that we're running. Parameterizations, what type of buoyancy that we're using. And in this case, we're using a TOS10 equational state, which is in seawater polynomials. Split explicit free surface, very simple advection schemes, and a z coordinate z vertical coordinate. Okay, so now we want to initialize the ocean model with data from Echo. The problem is that Echo requires a username and a password to download data. So I don't know, Gael, tell me if it's okay, but I created a username and a password that you probably can use, which is here if you want to copy this and put in your environment variables, then you can download data from Echo. So if you want, I don't want to really put it online, so it's just here if you want to copy it quickly. Otherwise, you have to follow the README in Oceananigans and in ClimaOcean that tells you how to register on the Echo website.
As they do that, I'll say maybe next week we can take a look at. I have another place where I have equivalent for these two.
Ah.
Publicly open.
Ah, well, that would be great if we can put that, because this is kind of a pity that you always have to register, and so we cannot really do something like this.
I agree.
But anyways, so you need these two environment variables: Echo username and an Echo WebDAV password.
That's why we use Signal.
Huh?
Isn't that why we use Signal?
Right. Okay. Somebody can take a picture and send it on Signal, and I go on. Okay. I guess everybody has the password. Let's go on. So now we initialize. Wait, let me. I have this one already in, so let me take it off. Okay. Ah, wait a second.
Sorry.
No problem. Is that I pre-run it and I loaded speedy weather at the end, so now it also went up. Okay. So what we're doing here is that this command will automatically download data from the Echo website. Temperature variable and salinity variable. By default, this is the first data point of the Echo dataset. So it's the 1st January of 1992. And when we initialize the ocean, we don't want to initialize with velocities, but only with tracers. So typically the ocean is always initialized at rest, and then since the major currents are all caused by difference in tracer gradients. If you initialize with tracers, it's fine enough. You don't have to add velocities. Okay, so let's look at the initial conditions that we defined. Here there's some Mackie visualization. So this is our initial sea surface temperature and our initial surface salinity regraded on the tripolar grid. You can see that the North Pole is here in this matrix, and this is Russia and this is Canada. So this is really these are the two numerical poles that have been stretched to be in land. Okay. Let's load the prescribed atmosphere. So this command will automatically download the prescribed atmospheric data from JR55. This is also quite heavy. So if you run it, this is about 10 gigabytes of data. So it will take a while for you to download. I'm just gonna run it as is because I already have it downloaded. So this framework will know that I have a stored atmosphere in scratch spaces. So it's gonna go and take it and interpolate it. Okay. And now I want to couple just the atmosphere and the ocean for the moment, just because when you couple the two components, you'll automatically compute the fluxes. So just to show you what the fluxes look like when you couple the ocean and the atmosphere. Taking a while. Okay, so we created the couple model, and while creating the couple model, already we have computed the fluxes between the ocean and the atmosphere, and they will look something. We can extract them, so they are in the couple model.interface.atmosphere ocean interface, and we can grab out the fluxes that we already computed. We have sensible fluxes, sensible heat, latent heat, X and Y momentum stress. And if we plot them, they look something like this. So here you can really see them printing out the atmosphere on the ocean. The negative means that is heating. So here the atmosphere is heating the ocean. At the poles the other way around. So the ocean is heating the atmosphere. And we have also some wind stress that is imposed from the atmosphere to the ocean. Okay, so this was only ocean and atmosphere, but now we need to add also the sea ice. So in this case, we can use again the grid that we generated for the ocean, because the ocean and sea ice run on the same grid. And we need to pass the ocean to the sea ice constructor, because the sea ice needs to know what is the surface salinity of the ocean, needs to connect to the surface salinity of the ocean to compute salinity fluxes, and needs to know the velocities of the surface of the ocean, because the stress is computed implicitly. And once again, we initialize the concentration, and this aleph is concentration, and this is sea ice thickness. We initialize it again from the ECHO4 dataset. There we go. And now we have also a sea ice component. We can check the ice thickness and concentration that we use to initialize the model, and looks something like this. So we have some thick ice on north of Greenland. This is probably north of Russia. Some ice in Antarctica. I mean, the grid is very coarse, but you can kind of recognize Arctic ice and Antarctic sea ice. This model for the moment is without dynamics. So the sea ice model can be divided in a dynamic and a thermodynamic component. The dynamic component is actually the heavy one, because the sea ice has timescales which are much faster than the ocean timescales. So it has to substep with respect to the ocean component quite a lot, and it's pretty computationally expensive. So especially for this resolution, we don't really need a dynamical component. So we specify dynamics equal nothing. Otherwise, by default, we'll use, for whoever here knows about sea ice modeling, we would use an EVP rheology, like elastoviscoplastic. Okay. Finally, we can couple the three components: ocean, sea ice, and atmosphere, all together. So now that we coupled also the ocean and sea ice, for the sea ice, it's very important to know what is the temperature on top of the sea ice. And this temperature has such a fast timescale that you need to compute it when you compute the fluxes. So now, while coupling the model, we don't only compute the fluxes, but we also compute the interface temperature between the sea ice and the atmosphere. Okay, here we go. So here we can access the fluxes between the atmosphere and the sea ice, which are in the same interfaces in atmosphere sea ice interface, dot fluxes. And we can also access the temperature between the atmosphere and the sea ice, which is a property of the coupled model. And they look something like this. I mean, not extremely beautiful, but the positive means cooling from the perspective of sea ice. So the sea ice, positive, means cooling. So the sea ice is growing here and here. And you can see that the temperature of the sea ice is about -40, -50 degrees Celsius. Okay, now we have all the components together. We can wrap the model that we constructed in a simulation object, give it a time step, give it a stop time, and attach some output writers. In this case, we're using a GLD2 writer, but we also have a netCDF writer. Attach a progress function that will just take track of where we are during the simulation, and then just run the simulation. But I think I will need to do this. Okay. Also this. Okay. So this will take a lot for the first time step, but it will be pretty fast once you have precompiled this first time step.
Yeah, that's a good question. Glad it's this morning. I had some problem with JLD2 on HPC cluster where you have a network file system. Did you have also some issues when you I think by default JLD is about MMOF to save data? But I have to use another way, maybe a slower way. Oh, sorry. So I'm wondering if you had issues GLD2 on a cluster with a network file system that you need to use another way to icing with IOStream, another option to use to save it reliably.
I never have problems in terms of saving or loading, but definitely performance issues.
Okay.
So the maybe it was just a cluster that I run on, but the loading and saving of files through JLD2 was very, very slow. So I don't know if that's really a JLD2 problem or is the network of the cluster I was running on.
Yeah. Okay, thanks.
Well, I thought I pre-run this, but apparently it's still pre-compiling everything. Does somebody have any other question, or did you manage to download, or?
Is it possible to run part of this workshop without the 10 gigabyte pausing?
Yes, you can. You need to add. Well, you can use SpeedyWeather instead. You can do the second part of the notebook.
Okay.
So instead of running the atmosphere, now I'm going to show when you use SpeedyWeather, you don't need to download an atmosphere, right?
Okay.
Because the atmosphere will be provided by SpeedyWeather. So if you just forget all this part from where you define an atmosphere down. Where did I define an atmosphere here? Here. If you forget about this and everything and all the rest of the cells that actually use this atmosphere, so till where we are now, basically, you can run it.
Okay.
So this is running, it will run.
So just outcome in that line, and then.
Okay, so this simulation is finished. 10 days of simulation. The output is extremely coarse and not so beautiful, probably, but you can check that something happened. So sea ice has melted a little bit. Temperature has increased a little bit. And if you want to see an evolution of the ocean sea ice, this is what happens roughly. Not much, but so in the ocean, 10 days are basically nothing. So 10 days for the ocean mean absolutely nothing. The ocean is kind of still for 10 days. So you have to run it probably for 2 years to see something, or maybe 1 year to start seeing something interesting. I guess we don't have 2 years here to run the simulation. Okay, so this you can run, Python Ocean model. So this is the new the new PR that has to be merged. That includes this Veros Python Ocean. So it's still a 4-degree ocean, and we couple it with the same JuliaEO25 atmosphere. So the only thing to do to actually load this ocean is we have an extension in ClimaOcean that implements all the methods that are required to extract the state variables from Python, communicate them to Julia, compute the fluxes, and send them back. And in this case, we're just using a preset global simulation from Veros. Veros provides already predefined ocean simulations that you can take and you can use. You can define your own setup, but you can also use predefined setups, and I didn't want to write in Python, so I just took theirs. And through Python call, we can install the Veros package. This is required because otherwise Veros will complain, and load this global 4-degree setup in an Oceananigans object, in a ClimaOcean object called Veros Ocean Simulation. And this is Python output, and we created Veros Ocean. Now we can couple it to a JuliaEO25 atmosphere, exactly like we did with the Oceananigans Ocean. So we define an atmosphere, we couple it with the ocean sea ice model. At the moment, the sea ice is not really supported with Veros, so I have to do some changing of the source code to make sure that also sea ice works with Veros. We wrap everything again in a simulation, spit out a progress file, and run the simulation. Here we go. Veros is a little bit faster to precompile than Oceananigans. This kind of hurts, but it's true. It's very fast to run. And here we go. 1 day of simulation with Veros coupled with an atmosphere. And we can see how the temperature looks like. This is a very, very coarse ocean, 4-degree, but something happened. So they actually opened very nicely the Indonesia throw flow. And Simon, maybe this is what you can run from here. Because this does not rely on downloading data for an atmosphere, because we use Milan's atmosphere. Okay. So let's go full on and use a dynamic atmosphere, dynamic ocean, a dynamic sea ice. All quite coarse. This is am I right? This is 400 kilometer resolution. 400 kilometers resolution, 3 vertical layers. At the moment, we can only do a full grid because of the XSMF package, and that will be solved with conservative regridding from Anshul. Putting you on the spot. Right. So we do the same thing. We reconstruct the ocean simulation, the atmosphere simulation. We reset the ocean we reset temperature and salinity in the ocean. And we take, for the coupled model, we now at the moment we take the atmosphere time step, but we can run also at different time steps for the ocean and for the atmosphere. Here we go. Okay, here we go. And we're gonna run this simulation with a 40-minute time step for 10 days of simulation. We have something to fix when it comes to radiation. I think Milan, you updated, right? But for the moment, I think we decided to put zero emissivity and zero emissivity because we need to fix the interaction of radiation from the atmosphere to the ocean and the sea ice. I think this doesn't even have sea ice, this model. Okay. It's taking more than usual. It's taking a while. Probably needs to precompile. Maybe you can just skip ahead. Because if it needs to precompile, we're gonna have to wait about 4 to 5 minutes. That's something that we have to solve, I think. Did somebody manage to at least start the first part? Yeah. Oh, okay, well, finally it started. So this is the output from Speedy Weather. And soon enough, we'll see also the progress. Oh no, we didn't add any progress. So this is just the output from Speedy Weather that is showing you what is the simulated years per day. That is increasing because, of course, the pre-completion took so much that we still have to recover from that. And in about 1 minute, the simulation will be finished. Okay, in the meantime, while this finishes, here we are visualizing the ocean sea surface temperature and the atmospheric state at the end of these 10 days coupled simulation. And the surface pressure. So come on, please finish. One, go. Okay, 10 days of simulation. Let's go. So we use NC datasets to load the NetCDF data of speedy weather. And here is the sea surface temperature of the ocean after 10 days of simulation, and the atmospheric temperature at the lowest level, and the surface pressure. Of course, the ocean doesn't show anything interesting because we ran it only for 10 days, and this is not a time scale in which anything changes in the ocean. Last part, interesting part, Veros plus speedy weather. So now let's couple speedy weather and the Python ocean, and this is the last simulation that we'll do. We do basically the same thing. We add Veros simulation, still going from using the global 4-degree setup. Speedy weather uses still 400 kilometer atmosphere with 3 vertical layers. Here we go. We couple the two, and then we run the simulation. It's slightly faster. How much did I run it for?
Is that the typical Veros speed at 400 kilometers?
Well, Veros is 400 kilometers. It's 4 degrees.
Yeah, but the 40 years per day, is that the typical speed?
I guess, yeah. It's truncated. I don't know why. And here we go. Same thing. The atmosphere does not really feel the ocean in 10 days. It doesn't feel anything. It just goes on by itself. And this is the output field from the Veros ocean. So yeah, this is just showing what we can do, what we can couple. I don't know if I have time to show. I actually wanted to show you how to build a custom slab ocean to add to the couple model, but I don't think I have time to do that since I'm here since 40 minutes. I thought I did precompile the ocean, but I didn't. So that's it. If you want to see how to build a component, you want to add your own component, you can follow this notebook. This actually doesn't require to download data, so probably I should have started from this one. But yeah, I guess that was it.